All right, so we're going to move on to chapter 11, which talks about radical reactions. Radical reactions are a little bit different than what we've seen before. So far in organic chemistry, we've always seen movement of two electrons in a pair rather than individual electrons. Radical reactions deal with the movement of single electrons. So the clearest way to demonstrate this is through bond cleavage reactions. There's two different types. There's heterolytic cleavage. So heterolytic means different, right? And this is what we've seen before. So if we have atom X and we have atom Y, we can have a reaction where X becomes a negative charge and Y becomes a positive charge. And when we do this, we know that this bond between X and Y is dumping both electrons onto X. So this is movement of two electrons. So movement of electron pair. And with heterolytic cleavage, we always get ions out. With homolytic cleavage, we get something a little bit different. Otherwise, people won't believe me if I told them you took organic chemistry. You got to have some evidence saying you took the test. All right, with homolytic cleavage, instead of moving an electron pair, we move individual electrons. So in this case, we have to show it differently with our arrows. And the way we do this is with fishhook arrows, which means it's a one-sided arrow. So one electron from this covalent bond goes to Y. The other one can go to X. And instead of getting ions out, now we get radicals, which means we've got an unpaired electron on each atom.
So is that just an electron on the...
Yep, you always draw a dot indicating that there's some unpaired electron on there. So movement of individual electrons. So it's a pretty simple concept. It's very easy to mistakenly draw a double-headed arrow, so you need to make sure that you're very careful with how you draw your arrows. Yep?
So when you draw the arrow on one side, you accidentally draw it on the other.
So in this case, you have to draw both arrows because we actually have two different electrons. If you drew it the other way, it doesn't matter. It just needs to be a single-headed arrow. So let's even make a point here, because this is something I see a lot with people, is that not all electron-pushing arrows are equal. A double-headed arrow means movement of two electrons, and this is not the same as a single-headed arrow, which means one electron. They look very similar, and people mistakenly draw double-headed arrows as single-headed arrows sometimes, but we do need to be very careful with how we draw them because they imply entirely different things. So let's take a look at an example of one of these reactions, specifically a cleavage of a covalent bond. So what I'm going to do is just label this as generic R groups and X groups with the central carbon. So we've got 3 R groups on here and an X group. And we're going to have this X group between the between the carbon and the halogen be cleaved in a homolytic fashion, meaning we're getting one electron onto each atom. And when we do this, we end up with an intermediate that looks a lot like our carbocations that we've seen previously. meaning that this carbon is now trigonal planar. And we've got an electron in that empty p orbital, and now we've got this X atom also with a single electron. So just like with carbocations, we go through this trigonal planar intermediate. And the stability trends are all exactly the same as with carbocations, right? So we follow same stability trends as with carbocations. So with carbocations, we saw that the more substitution we had, the more stable they were, right? Tertiary carbocations more stable than a secondary, and that's more stable than a primary. Why is that the case? Hyperconjugation, right? So if we have adjacent sp3 orbitals in one of those R positions, they can help stabilize that empty p orbital, or in this case, a p orbital with one electron in them. In the book, they briefly indicate that this can oftentimes be slightly pyramidal, meaning it's not quite planar, but they rapidly invert between this very shallow pyramidal state. As far as we're concerned, they're very, very close to planar. And so as far as we know, they're going to be trigonal planar. So I'll put a little asterisk there because the reality is they're not perfectly planar. Oftentimes that electron will actually repel it slightly down a little bit. All right. With resonance structures of radicals, we have to pay particular attention to our electron pushing arrows. So let's quickly go over resonance structures for radicals. We can have regular plain resonance structures with radical reactions, but this time we're going to be moving electrons one at a time, not in pairs. So we're going to draw them a little bit differently. And I'm going to show an example molecule. Oh, sorry, I need to shut off my email. And in this case, I'm going to draw in each and every hydrogen atom. In this case, I'm going to draw this hydrogen atom as blue, these terminal ones as green, and let's do this one over here as black. If we have a homolytic bond cleavage of this green proton, we can have one electron hop over to that hydrogen, the other hydrogen hop over to the adjacent carbon, and now we get a homolytic bond cleavage. If we do that, now we've got two hydrogens in that position, along with a radical. And I'm going to try to keep the color scheme all the same here. And then we've got the remaining two green protons. And we popped off one of them, so it will be hanging out on the left as its own radical. The thing we have to pay attention to is that that radical wants to delocalize, especially if there's an option available. Just like with anions, we know that anions aren't that stable, but they're a lot more stable if they can delocalize. The same is true with radicals.
So it's just one electron there.
Yep, one electron. So this electron can try to jump into an adjacent bond, and the pi bond right next to it can contribute one electron, so we can move one over there. So now we've got two electrons moving into that carbon-carbon position, and the remaining electron from that pi bond will want to jump over to an adjacent carbon. So we've got three different single-headed arrows, and now when we do this, oh my goodness, sorry. The life of an academic, all emails. Oh, I've got my double bond on the wrong side. So now we've got the electron on the right carbon. And we've got this radical completely delocalized. In this case, it can either reside on the left carbon or the right carbon. If you remember back to our section on resonance structures, it's not that it's constantly flipping back and forth. It's more of a hybrid between the two. And in this case, that means that the left and right carbon have to be sp2 hybridized in order for this delocalization to occur. So it must be sp2 hybridized to allow for delocalization. Which goes back to that same idea of us saying that when we've got a radical, it's got to be that trigonal planar intermediate. Yep.
What has to happen for these reactions to occur?
What has to happen?
Yeah, like low temperature.
We'll talk about that more, initiating radical reactions. But for right now, I just want to cover the basics of what is a radical, how do we judge its stability. The other thing I wanted to mention was that these protons in particular have a very specific name, these green ones. These are called allylic protons. And allylic protons mean that they're on the carbon that's adjacent to a double bond. So if you look at our double bond, you go one carbon away, you're running into those protons. Anytime you have an sp3 hybridized carbon, one carbon away from an alkene, it's going to be in the allylic position. If we look at the top position with this blue proton, this is going to be called the vinylic. Vinylic protons don't like to undergo radical cleavage because they don't have any resonance stabilization. So in this case, we're primarily concerned with the allyl protons and forming allylic radicals because they're extraordinarily stable. So in this case, there's two things that can stabilize radicals. So two things can stabilize radicals. The first is hyperconjugation. So how substituted the carbon is. And the next one is resonance delocalization. So just like with ions, we can try to delocalize the charge, and by delocalizing it, we can stabilize it quite a bit. Sorry, I'll move this up for you guys. So let's practice doing a resonance structure because sometimes they are a little tricky. We haven't seen single electron pushing. So let's take this one, a cyclohexene derivative. And we've got a radical on that top carbon of the cyclohexene. How can we delocalize it? Can we push it to the left? No. In this case, it's also important to notice that where is that radical? Is it on the vinylic or allylic position? Allylic, which means that it is incredibly stable. So this will want to dump in, form a double bond. This double bond can push over, form a double bond there, or contribute to the pi bond that's forming. And then this remaining electron in that pi bond will just get dumped on that neighboring carbon. So with a lot of these resonance structures, you actually have to draw 3 arrows. Yep.
Does it want to do it too, like the most stable carbon?
In this case, we can just draw it delocalizing to any position where resonance is allowed. There will be major and minor contributors, just as with resonance structures. So the major contributor will have the radical on the more substituted position. Yeah. All right, so let's draw the product we get. Oh. Now we've got the double bond here. Oops, sorry. here. And we've moved our radical over into a more stable tertiary position. Can we do any more delocalization?
Probably.
It's still allylic to the other double bond, right? So let's try to draw the electron pushing here. So we've formed a new pi bond, and then with that remaining electron, it'll go out to the next carbon. So we've got a double bond here, and we've got our radical out on the very end. With any resonance structures, we have to be sure to bracket it to indicate that it is in fact a resonance delocalization and not some sort of reaction. Yep.
So with the structure on the right, even the least.
Yeah, let's go through and look at our major and minor contributors. So in this case, this one will be our major contributor because it's got the radical in the more substituted position. This one will be a minor contributor, and this one will be a minor contributor. The one on the far right will be the most minor contributor because it's on the primary position, but we're not going to try to distinguish those two frequently. We're primarily interested in the most major contributor, or majorist. I'm not sure how you'd pronounce that. Yeah?
So why don't you draw the final one again? The far right?
The far right?
Yeah, that's where this focus.
So with resonance structures, we just need to remember that it can delocalize across all three of those positions. The major contributor is going to be that middle one. All right.
Why don't you do it again to that last one?
So if we look at the last one, we can push that electron to the left,
Yeah.
but if we do that, we just get to the other two structures that we had before. So these are the only three possible structures we can get. Yep.
Is this only possible with the help of the double bond?
Yes. Unless you're going to cleave a single bond, in which case that's not a resonance structure, that's just a reaction. So just like with resonance structures from our first term, you shouldn't break single bonds. So in this case, you really only observe resonance structures when there's double bonds, particularly allylic double bonds, right, or allylic radicals. With triple bonds, we're not going to get into that. There are some examples of triple bond reactions involving radical intermediates, but this chapter focuses primarily on double bonds. Yep. All right, so the reaction classes are pretty similar to what we've seen before. They tend to fall into lumps. Actually, let me change this. Types of radical reactions. The first one is cleavage, which we already saw, but I'll show it again. So if we have X bonded to Y, we can have one electron go to X, giving it a unpaired electron, and we can have one electron go to Y. And we said in order to show that, you have to do a single-headed arrow going to each. Conversely, you can have coupling, right? So we've got two radicals. These radicals can do the reverse reaction. So if we've got a radical X and we've got a radical Y, I'm going to actually erase that, we can have these two electrons try to find each other and form a new covalent bond. So it's just the reverse reaction. Because these are in the same family, I'm going to just box them in together and say they're very, very similar. They're just the reverse of one another. So these deal with single bonds only. So are we making or breaking a single bond? We can also have reactions with pi bonds, though. So let's take a look at reactions with pi bonds. We can have addition to pi bonds. Nope. So imagine we've got some sort of radical X, so X dot, and we've got a pi bond. And I'm just going to label that as a normal old-fashioned pi bond. We can have one electron come down from the radical and another electron come over from that pi bond, and we can form a new covalent bond. the other electron from that pi bond will get dumped over to the carbon on the opposite side. And our final product will have the new covalent bond, another sigma bond, and then a radical on the very end. So we haven't created or destroyed radicals. We've just turned one radical into another radical by pushing single electrons. Conversely, we can have the opposite reaction, which is called elimination. So if we've got X on the end here, and we've got our radical, we can say, all right, this can dump down one of these electrons from that covalent bond can dump down, and then the other one can just hop back over to X. And if we do this, again, we're just doing the reaction backwards. So we get our X radical and our pi bond out. So these are another class of reactions that involve addition or elimination resulting from or giving a pi bond. The last class is the most unique class that we haven't seen before, and this has to do with abstractions. So the first one is called hydrogen abstraction. And with hydrogen abstraction, you have some sort of radical. I'm just going to call it X. And then you've got a hydrogen attached usually to some sort of alkane. What will happen is this radical will steal the hydrogen. So the radical electron will come over, the electron from the covalent bond will jump over, and then the remaining one will jump onto the alkane. And when we do this, we now get a new covalent bond between X and our hydrogen, and then we get a radical alkane. So hydrogen abstractions we'll see in a few different reactions, but it's the transfer of a hydrogen atom from an alkane to some sort of radical. The other one we see quite a bit is halogen abstraction. And in this case, you start out with a radical alkane, and then you have some sort of halogen. And in this case, I'm just going to call it XX. And with these reactions, it looks very similar. The radical alkane will give one electron. The covalent bond will give one electron to form a new covalent bond. And then the remaining electron from that covalent bond will jump over to the halogen. And so instead of transferring a proton, now we're just transferring a halogen. And the resulting byproduct is a radical halogen. So these are their own class of reactions too. Using these 6 different types of reactions, we can do quite a bit of chemistry. And this is the basis for a lot of modern polymer chemistry. We're going to talk a little bit about that tomorrow, but we're going to try to get into the basics of these reactions today. The one thing I want to say too is for halogen abstraction, this is almost exclusively observed with bromine and chlorine. I mentioned before that fluorine is very, very reactive. Oftentimes these reactions are not selective with fluorine and very, very exothermic, which means that they're dangerous to perform and not that useful. So in the book, you almost exclusively see bromine and chlorine. Thermodynamically, using iodine is not favorable, so you don't see radical reactions with iodine very often. All right, so we've got our steps down. Let's start to do some new reactions with these. And the most useful reaction is called halogenation. Oh. Oh, shoot. Yep.
Do you remember when we took the quiz and you said that maybe for the test we could have like the reagent?
If I give you a complicated problem, I'll try to guide you through it by giving you some hints.
Okay.
But I want you guys to know the main reagents that we've covered from 9 and 10.
Okay. Sorry that this came out wrong.
That's okay. Before starting the halogenation of an alkane, I always recommend looking at your alkane and assessing it a little bit. So let's take an example of your alkane. And we'll get a before starting list of instructions. Before starting, you want to identify a proton in a position that would result in a stable radical if removed. So identify a proton that would result in a stable radical if removed. And I'll explain what I mean by that by using an example. So let's say we've got this alkane. It's a cyclohexane. So we've got methyl cyclohexane. We've got a variety of different protons we can look at. So let's kind of work from the interior outwards. We've got protons in these positions, and I'll label these red. So they're on a secondary carbon, right? If we look at this carbon here, it also has a proton. We'll label that blue. That's on a tertiary carbon. And if we look on that methyl position, whoops, we've got 3 different protons, and I'll label those green. And that's on a primary carbon, right? So we could remove any one of those protons if we wanted to, and we can see what the radical would look like. So let's say we move the green one down here, and then I'll get another arrow where we move the blue, and then another one where we move the red. So I'll do minus H dot, that's green, minus H dot, that's blue, and then minus H dot, that's red. If we remove the green one, we form a primary radical. If we remove the blue one, we form a secondary radical, or sorry, tertiary radical. And if we remove the red one, we form a secondary radical. Which one's going to be the most stable? Tertiary. Tertiary, right? So in this case, this is the most stable radical. So we know that this is the position that the reaction's most likely to take place at, and we can determine that even before we start the radical mechanism. Yep?
Are radicals actually stable compounds?
That's a really interesting question. For a very long time, people said that radicals are very unstable, just like a carbocation is unstable. But there are some radicals that you can buy that are so stable you can just store them in a jar. They can be open to air even, and they don't decompose, they don't react, they're very inert. An example of one of those radicals that's very stable is tempo. And we'll talk about that more because we're going to be using it in next week's lab period. So we're going to be able to use a very stable radical in one of our reactions. So we'll talk about that in the pre-lab lecture. All right. Now let's get down to the nitty-gritty of this reaction. So the first step is we have to somehow form a radical, and that's called an initiation step. So first step is initiation. And initiation of a radical can be achieved a couple different ways. Let's take the example of bromine. Actually, I'm sorry, let me take this back. Let's do chlorine. I know, I'm ruining everyone's notes. Here we go. In order to get one of these electrons over to one chlorine atom and another over to the other chlorine, the most traditional way to do this is to expose it to heat, which doesn't work very well. Or the better method is to expose it to UV light, which we just indicate with HV. So you can get a mercury bulb, turn it on in your fume hood, have it shine over your reaction, and it will actually cleave weak covalent bonds into radicals. It's also a reason why we try to avoid UV when we're outside, right? If you're standing outside and you're being hit with all these UV rays from the sun, you're going to get radical reactions going on in your skin. Sometimes those radical reactions can result in cancerous cells, and it leads to a bunch of health problems. So UV works very well for trying to start radical reactions when you want them to occur.
If you're doing it in the hood, can you see it with like a microscope or something, or with whatever?
So you turn on your mercury bulb, and then usually you have some sort of UV shield between you and the bulb, so you're not being exposed to the UV, only your reaction is.
Yeah, but can you see it if you like recorded it somehow?
The UV light?
No, the turning into a radical.
Sometimes you'll observe a color change. It depends on the radical. So in this case, we've taken elemental chlorine and we've converted into 2 chlorine radicals. Now the second step is called propagation, which means we're going to turn one radical into another. So with propagation, you can imagine, all right, let's say we've got our our typical alkane, and I'm going to label this terminal group CH3 and this one hydrogen so we can tell them apart. And we formed our radical chlorine. What we can do is have a hydrogen abstraction, which we saw on our last slide. So this chlorine will give its electron, this covalent bond will give an electron, and then the other electron will get dumped down to that adjacent carbon. Now we're forming that stable radical that we analyzed before we even started the mechanism. And we know that this radical is trigonal planar, right? And we've formed hydrochloric acid. So let's just put down trigonal planar radical. And so we've turned this chloride radical now into an alkane radical. This alkane radical is very, very reactive. So it can do a couple different reactions. The most common of which is going to be a halogen abstraction. So now that we've got this, we can say, all right, let's assume we've got some more Cl minus in solution, or not minus, Cl dot in solution. This can attack from either face, and we can form a new covalent bond.
Where'd that one come from?
Actually, let me change this a bit. I'm going to do it in 2 lines just to make it more clear. Sorry. So we've got CH3. And this time, we're going to have it react with elemental chlorine just to show that this is, in fact, a propagation. So this will be a halogen abstraction. And then the other electron gets kicked off onto the chlorine. And when we do this, we now get halogenation at that most stable radical position. So we got CH3 here, Cl. In this case, we could have done a top face attack or bottom face, but the carbon that the attack's taking place at isn't a stereocenter, so it doesn't matter. And with any propagation, we always remake a new radical, so we've got Cl dot here. So this is our product of interest. So we can actually put a halogen onto alkanes by performing a halogenation reaction as long as it's a radical halogenation. Yep?
Will the chlorine radical in that do it again with the other?
That's a good question. So in this case, the last step is termination of a radical. So we do have a radical that's very reactive. If we want this reaction to stop here, we need to kill it somehow. So we call that a termination reaction. If we have excess chlorine around, this will keep on chlorinating until it exhausts itself. Oops, sorry, this should be third step. Third step is termination. And there's 3 different options for termination. When you draw the mechanism out, you can choose any 3 of these options. I really don't care. I just want you to show the radical dying somehow. Just have an arrow, dead radical. All right, the one option is if you've got 2 chloride radicals nearby, these can couple together and terminate. And we can reform our chlorine gas. Okay. The other option is we can have our alkane radical react with some extra chlorine radical and produce more product, which is desirable. I'm going to put CH3s on here so we're being consistent. Or the last one, which is undesirable but oftentimes a byproduct, is you can have 2 of your alkanes coupled together. In this case, it's not going to be very likely because we know that this would be a very, very sterically crowded reaction. But theoretically, you can imagine these 2 alkanes coupling together and forming some covalent bond if it were possible.
If it were possible, then why are we?
There are some situations where this coupling is possible. I'm just telling you guys that for this specific reaction, the coupling of these 2 radicals would be very sterically crowded, so it wouldn't be the most likely option, but it's theoretically possible.
Although you don't care of the options, which can be best.
Usually the one I draw is the second one because all we're doing is making more product in that termination step. And so this is one mechanism that would be perfectly fine. Most people don't care. The bulk of the mechanism is in that initiation step where we're cleaving the chlorine, and then the second step where we're propagating it and then getting our product of interest. The thing is, we're not quite done. Kind of like we're not done when we have a last deprotonation step. We have to show that last deprotonation, just like we have to show termination of a radical. And somebody brought this up earlier, and they said, well, what if there's excess chlorine around? If there's excess chlorine around, it will just keep on adding to the next most stable radical position until it runs out. So if excess X2 is around, it will add to the next most stable position. No, this is just for the overall reaction. So if we go up at the top and we look at these red, blue, and green protons, if we do the first chlorination, it's going to occur at that blue proton position. But if we have another equivalent of chlorine around, it will occur at one of the red proton positions. So we can try to over-chlorinate or polychlorinate our compound. This is actually the method that they use to produce dichloromethane, which we use in lab. So you can take methane, natural gas, do a radical chlorination with chlorine gas, and you can add on 2 chlorines, right? So you do a double radical reaction. So they add in 2 equivalents of chlorine gas, and they're able to add 2 chlorines to methane to get dichloromethane. All right, so let's talk a little bit about the regiochemistry here. We talked about it to some extent, saying that if we look at the site of interest, we know that it's going to be the one circled in blue, right? Because it's the more stable radical. But there's a little bit more to this story. So let's talk about regiochemistry. let's say we've just got a simple tertiary carbon, right? And we react this with chlorine, so Cl2 and UV. The main product will have chlorine added to the more substituted position.
Is that HV or UV?
UV. Or sorry, HV.
But it's for UV. Why don't we just write UV?
Some people write UV, some people do the physics abbreviation HV. Yeah, I'm fine with either. I just wanted you guys to see how it's done in the book. The other option we said is that there is a chance of it reacting at the less stable radical. Although the chance for chlorination is pretty small. If we run this reaction, we get far and away reaction at that more stable radical position, which is 72%. At the less stable position, we get a 28% side product. So with chlorination, it's a little bit harder to control. But if we look at bromination, bromination is a really nice reaction. If we do this reaction with bromine and UV, we get bromine there, and we can imagine the minor product. But in this case, bromine almost exclusively adds at the more substituted position, and almost none of it adds to that less substituted position. So bromine in this case is much more regioselective than chlorine is. Bromination is more regioselective than radical chlorination. So oftentimes people will choose the bromination route because it leads to a much cleaner reaction. You don't get a mixture of products. All right, so let's take a brief look at stereochemistry. The stereochemistry is fairly intuitive. And the stereochemistry should remind you a lot of the stereochemistry for carbocations. And so let's do a brief reaction here. Yeah, just 1 second.
Yeah, you just leave the bromination. You can still do the stereochemistry. Just leave that bromination section.
Okay, leave this one?
Yeah, just the words.
Just the words. Like that. All right. There we go. All right, so if we do a bromination here, under UV conditions, which carbon is the bromine going to add to? It's going to be the third carbon, or I'll just label in a red, right? So that red carbon's the more substituted position, so that's the site that the halogenation is going to take place at. And if we do this, I'm going to draw out the skeletons really quick. We get one situation where the bromine can add from the top face, moving this CH3 group to the back. Or the bromine can add from the bottom face and the CH3 group can be pointing forward. Right? So let me fill in CH3 here so we're being consistent. And in this case, we get a racemic mixture. Why are we getting a racemic mixture? Because why? It's not a substitution, right? So if we go back up to the mechanism and we look at this step, we've got a trigonal planar radical, right? Can this chlorine add to the top face or the bottom face, or does it matter? It doesn't matter, right? So in this case, because we go through a trigonal planar intermediate, we lose our stereochemistry and we get a racemic mixture of products. So the mechanism goes through a trigonal planar radical resulting in a loss of stereochemistry or a scrambling of stereochemistry. You make a mixture of products. All right, so I think that's where we're going to leave it today with the problem of the day. I ask you to go through and do the mechanism for a radical halogenation reaction. And then I also throw in a reaction from a previous chapter. So you may need to take a look at one of our previous chapters to do the second step, but please draw the whole radical mechanism in the big box on the bottom portion of the page. All right, also lab will be open today, so if you need to come in and get your master melting point, please feel free to stop by.